Okay, good.
Yes.
So let's, all right. All right. So I need to give some quick background. The title is Open Questions in Mereotopology. So I want to briefly say something about that. And in particular, I want to distinguish the kind of questions I'm interested in today, which are questions in mereotopology, from questions about mereotopology. I take it that I hope everyone here is familiar with the very notion of mereotopology, but here are some examples of questions that are interesting, open, perhaps even typical questions about mereotopology that I'm not going to discuss, but I think are going to be in the background for most of what I've been saying, and they're probably also in the back of your mind. So, for example, is it a piece of formal ontology? Obviously, at your institute, at your center, this means a lot. It depends, of course, on what you mean by formal ontology, and you obviously have a serious project and a serious program. I myself tend to be thinking of formal ontology in Husserlian terms, so I still think of it as a field of research where we try to figure out the general principles that govern what there is, no matter what it is. But if you have a different conception, that's perfectly fine. So one of the general questions about mereotopology is whether it fits the bill. Secondly, of course, you may be interested in mereology and in mereotopology from a, say, Lesniewskian nominalistic perspective. And so you might think of it as potentially a good alternative to set theoretic topology. So topology built on or erected upon mereology rather than on set theory. How far can we go, etc.? Those are interesting questions. I'm not going to talk about that. Also, you might be interested, and I'm sure some people present today are interested in whether we get a good notion of wholeness by considering mereotopology. Given that, despite a certain way of referring to it, mereology is only a theory of, only concerned with parthood. Sometimes it's referred to as the theory of parts and wholes, or of the part-whole relation, but really there is no notion of wholeness in mereology, and so you might think that topology provides a suitable supplement to the work done in mereology and deliver a suitable theory, a suitable notion of wholeness. These are examples of open and typical questions about mereotopology. Leave them in the background. I'm more interested in questions that arise, as it were, within the framework of mereotopology. For example, first of all, with parthood and connection, which I take to be two good examples of, respectively, a mereological and a topological primitive. With these notions axiomatized in their own terms, what sort of bridging principles should govern their interaction? Second, there are, as you know, several non-equivalent ways of defining composition, mereological composition, in terms of parthood. So what other options are there in a broader mereotopological setting? Or there are several ways of regimenting mereological decomposition in terms of parthood, including, for example, whether we want our mereology to be atomistic or anti-atomistic, gunky. What other options are there in a mereotopological setting? And once you have those general questions, you can ask even more specific questions. For example, under what conditions can we recover the notion of a self-connected entity? Under what conditions can we recover standard topological concepts and principles on a mereological basis? For example, the distinction between open and closed entities, or the Kuratowski axioms for closure and interior operators, or for that matter, under what conditions can we recover the distinction between a whole with holes and a whole without? So here you see the two ways of spelling the word whole. I've been in my life concerned with both. It's a very unfortunate curriculum, because whenever I use the word, I have to specify whether I have the W or not. Today we'll be interested mostly in holes with the W, but as some of you might know, I also have a passion for holes without the W. And I'm always in trouble because in English, apparently the theory of holes with the W is called holology without the W. And my life has been a mess as a result of that. Anyway, so these are good examples of what I take to be open questions in mereotopology. Some of them have been, of course, on the table for a while, but I think they're still, all of them, open questions. I will focus on only 3 of them. And in particular, the third one is the one that I advertised most explicitly in my abstract, but I do want to say something about the first 2 that I have highlighted here. So bridging principles and composition notions. So let me move immediately to the first type of question, which is really meant to serve as background for the remainder of the talk, but still it will occupy us for a bit of time. So with parthood and connection axiomatized in their own terms, so both treated as primitive notions, what sort of bridging principle should govern their interaction? That's the first question I want to discuss. So I'm going to assume that we just treat these notions as binary relations, as expressed in binary relations. So pxy for x is part of y, cxy for x is connected to y. Of course, there are other primitives one might consider, as there are other ways one might think of these notions, for example, as a 3-place relations, if you want time to be explicitly represented, perhaps as 4-place relations, if you want worlds or modality to be also represented. But I'm not going to go through any of that today, so we're just going to stick to a very simple treatment of these notions as binary relations. Also, I'm going to work within a very simple first-order logical framework. As some of you know, this isn't quite right if you want to have sufficiently strong principles of composition, but for our purposes, it doesn't, the complication doesn't matter, and it'll be easier to stick to a first-order approximation, let's say. So, what principles? What kind of bridging principle? First of all, what kind of principles do govern these 2 notions? With respect to parthood, I'm going to assume, for the sake of simplicity, that it is a partial order. So it's a reflexive relation, a transitive relation, and anti-symmetric. I'm well aware that each of these assumptions is less uncontroversial than one might think, and then I myself used to think. But let's bracket any worries we might have about these principles. I'm going to assume that P is such a relation. As you know, in addition to characterizing what kind of relation parthood is, to get a mereology, you need to say something more. There are lots of partial orders. So in particular, you need to say something about composition and decomposition. But first of all, let me make sure that we also understand some additional notions that I'm going to use. Proper parthood is just parthood without identity. That's the relation you see at the top. The circle is a proper part of the square. Overlap, when they have a part in common, that's the middle case. And disjointness is just the opposite, when they have no parts in common, corresponding to the third case. So I take it that everybody's familiar with this. Then plug in your favorite composition and decomposition axioms. I say your favorite because I'm well aware that here there is plenty of room for philosophical and not only philosophical disagreement. If you like classical mereology, then you're going to have as your fusion axiom and axiom schema of unrestricted fusion to the effect that whenever there are some things that satisfy a certain condition phi, there is something which is the fusion of every phi. The notion of fusion that I'm defining here at the bottom is the one that Aaron and I used in our textbook as the main notions. It's basically just the least upper bound. So Z is the fusion of the phi if every phi is part of Z, and if Z is part of anything that has that property of containing every phi. So just the least upper bound with respect to parthood. Classical mereology assumes that every non-empty collection of things, any bunch of phi's, has a fusion. So that's unrestricted fusion or unrestricted composition. And if fusion is defined this way, to get classical mereology, you need your decomposition axiom to be a remainder axiom to the effect that if X is not part of Y, then there is something which literally is the difference between X and Y. So something whose parts are exactly the parts of X that don't overlap Y. I don't know if you're familiar with this machinery or not. This that you see right now is classical mereology, but as I said, we don't need to assume, of course, to do mereotopology, the full strength of classical mereology. Plug in your favorite composition and decomposition axioms. The next thing is the connection relation. And typically here, one starts by saying that, first of all, it's obviously not a partial order because it's not transitive. So say France is connected to Germany and Germany is connected to Poland, but France is not connected to Poland. So it's not transitive. It is, however, reflexive. Everything is connected to itself. And we may suppose that it is also symmetric. If X is connected to Y, then Y is connected to X. So France is connected to Germany. Germany is connected to France. So these two principles are usually taken to be basic and uncontroversial. What other notions can we add? What other axioms can we add? One option here would be the following. You may like the notion of enclosure. X is enclosing Y whenever what's connected to X is also connected to Y. Some people even think that enclosure is parthood. So there is a tradition going back to Whitehead's Process and Reality, very popular among people doing mereotopology in old-fashioned AI when you were concerned with spatial reasoning and so on. And most theories in that domain tend to define parthood in the way in which I've just defined enclosure here, and therefore to reduce mereology to topology. I'm not going to do that, but surely the notion of enclosure is worth mentioning. It is, by the way, by virtue of logic alone, a relation that is reflexive and that is transitive. If you want, you may even think of it as a relation that is anti-symmetric. That has to be added. It would be a third axiom. So things that are enclosed in each other are identical. But if you have that, notice that you immediately get as a theorem that the connection relation is extensional. So things that are connected to the same things or by the same things are identical. That's a very strong principle. And my understanding is that not many people want to have such a principle, especially if you, for example, endorse a metaphysics or an ontology that makes room for collocated entities. If you distinguish, for example, the statue and the corresponding lump of clay, I don't, but some of you might do that. And then you might think that they're connected to exactly the same things, and yet, of course, they're distinct. So this kind of extensionality isn't good, even though you might want to preserve a mereological extensionality, even in the spirit of a framework that allows for collocated entities such as the statue and the clay. So I'm not going to push this line, although I do want to mention this possibility, but this gives you a very specific mereotopological theory as opposed to a broad mereotopological framework, which is, I think, the better starting point. So eventually you might want to go this way, but first I think we really need to look for some way of connecting the mereological part of the story and the topological part of the story insofar as they are relatively uncontroversial. Is that a noise signaling a question? Is that a question? No. Okay. So one obvious good candidate would be what I call here integrity. If X is part of Y, then that's a sufficient condition for X being connected to Y. So my hand is part of my body. My hand is connected to my body. In fact, if you have that principle, reflexivity of connection becomes redundant given the reflexivity of parthood. Even stronger and equally plausible, though, would be the principle to the effect that if X overlaps Y, then X is connected to Y. In other words, overlap is a way for things to be connected, even though there may be things that are connected without actually sharing any parts. They would only share, so to speak, a boundary. In fact, this is perhaps one of the most important and interesting notions that we got from Whitehead, the notion of external connection that you see defined here in D6. So X is externally connected to Y precisely when we have a case of connection between X and Y that is not a case of overlap. And once you have that possibility of things being connected without overlapping, you may define other notions, for example, the notion of internal parthood or the notion of tangential parthood, which would in fact allow us to increase in important ways the map of mereotopological relations that we saw earlier within the purely mereological framework. So here at the top, I don't know if you see my cursor, but at the very top, you would say that the circle is an interior part of the square, whereas just below, the circle is a tangential part of the square. So in both cases, we have a case of proper parthood. Mereology doesn't distinguish those cases, but topology or mereotopology allows you to distinguish those cases. Similarly, the third pattern is a case of overlap. The fourth is a case of external connection. And external connection and disjointness are mereologically indistinguishable. In both cases, there are no parts in common, but they are topologically distinguishable. So it is precisely because of this variety of relations, and there are many more, that we could, in fact, define at this point, for example, connection by a point versus connection by a line, etc. It is precisely for this reason that mereotopology has been considered an important contribution when it comes to spatial representation and spatial reasoning, and more generally to formal ontology in some sense of the expression. Now, a third important principle here would be what I call monotonicity, to the effect that if X is connected to Z and Z in turn is part of Y, then X is connected to Y. So if I hold the glass with my right hand, the glass is connected to my hand, Z. My hand, Z, is part of my body, Y. Well, then the glass is connected to my whole body, Y. Very intuitive principle. In fact, if you have this principle, both unity and integrity become provable, provided that we take back our reflexivity axiom for C, which is really a better way to have it. So we go back to having C1 and C2 as axioms governing the principle C by itself, and monotonicity would be a very natural bridging principle, which entails both integrity and unity. In fact, you don't need to have that formulation. A better formulation, perhaps more intuitive, would be this one. if there is a part of y such that x is connected to it, i.e. if x is connected to a part of y, then it's connected to the whole of y. And indeed, it's enough to have proper parthood, because with parthood, that principle is kind of trivial. So the idea is, now given in this form, if x is connected to a proper part of y, then it's connected to the whole of y. Now, in this form, my understanding is that the principle is fairly recent. It was only put forward 20 years ago. I say fairly recent, given the moderately longer history of mereotopology. But in Xinqian Tsai's dissertation on mereotopology in 2005. I like this principle, so I strongly recommend that if you're interested in mereotopology, in addition to C1 and C2, you actually endorse B1. An interesting question is whether you want to have also the converse principle. If X is connected to Y, is it bound to be connected to a proper part of Y? If you're connected to me, does it mean that you have to be connected to some proper part of me? Well, in a way, I would like to say yes, but provided, of course, that Y is not atomic, because if Y is atomic, then it doesn't have any proper parts. But if Y is not atomic, so if it is a complex composite entity, then it sounds like a very plausible principle. In fact, in this form, I think I would recommend it, and it can be put as follows. If X is connected to Y and Y does have some proper parts, then X is connected to one of those proper parts. And in this form, it's sometimes called demonotonicity. And the first time I saw it in the literature is in a paper by Ben Blumson and Manikaran Singh, published 5 years ago. I think the package that you see here, C reflexivity, C symmetry, and then both monotonicity and demonotonicity, constitutes a fairly nice, elegant, general, and I would say uncontroversial framework for mereotopology, or rather principles to be added to mereology to get a mereotopology. And this is what I would like to offer as the most neutral framework. The interesting question, and I'm going to leave this question open, is what else? What else do we want? So, for example, do we want C extensionality? What else do we want? Anyway, that's the sense in which I call this an open question. It took some time to work out B1 and B2 in the literature, but clearly the theory is still fairly weak. In the book that Roberto Casati and I published many years ago called Parts and Places, we had a certain theory that we called, I forgot, but something like general extensional mereotopology, GEMTC or something. That was even weaker than the theory you see here. But even this one is, I think, not strong enough to, for example, offer mereotopology as a reasonable alternative to point set theoretic topology. So that's our first question mark. Let me move on quickly to the second issue, and this is fairly simple, in order to then finally address the third and I think most interesting question. So composition. Here the question is, there are several non-equivalent ways of defining composition in terms of parthood. What other options are there in a mereotopological setting? Here is what I mean when I say that there are several ways of defining mereological composition. Earlier, when I illustrated one way of formulating classical mereology by adding a principle of unrestricted fusion, I used the notion of fusion that you see here at the top, which I said is just the least upper bound with respect to the parthood relation. In the book with Aaron, we call this algebraic fusion, precisely because it's just the least upper bound. Some of you may be familiar with other notions. For example, it's very common to rely on what is here listed as F2, the Lesniewski notion, because this is indeed the notion that goes all the way back to Lesniewski's 1916 original formulation of mereology. You know that the term mereology itself comes from Lesniewski, even though only introduced in 1927. But the 1927 version of mereology is just a formalized or semi-formalized version of the 1916 theory, and their fusions are defined this way. So Z is the fusion of the phi, of the phi's. For example, Z is the fusion of all the cats, means that every phi, every cat must be part of Z, and every part of Z must overlap some phi, must have a part in common with some cat. That's a very common notion. When Peter Van Inwagen formulated the so-called special composition question, under what conditions do certain things compose something, a question which gets the answer any condition in classical mereology. Well, when he formulated that question, he used essentially this version of composition, this notion of fusion. The third notion that I list here is also very common. It was, for example, used by Peter Simons in his very famous and influential book, Parts, through which most of us know mereology. This is a notion that goes back to Goodman's The Structure of Appearance, and it's very similar, except for using overlap rather than disjointness, to the notion used by Goodman together with Leonard in their Calculus of Individuals. It says that the fusion of the phi's Z, that Z is a fusion of the phi's, just in case the things that overlap Z are exactly those things that overlap one of the phi's. So the things that overlap the fusion of the cats are exactly those things that overlap at least some cat. Now, these three notions are all very intuitive. David Lewis, in his book, Parts of Classes, actually lists all of them in the context of a single paragraph, basically treating them as expressing the same idea, but they're not equivalent. That is to say, they're not equivalent, logically speaking. And here you have three diagrams. I'm not going to go through the details because this is presumably well known to most people, but you can find scenarios such as the one on the left, where something Z is a fusion of a bunch of things, in this case, A and B, in the first sense, the algebraic sense, but not in the other senses. So Z here is the least upper bound of A and B, but it's not a fusion of A and B in the Lesniewski or in the Goodman sense. In the middle diagram, you get the absurd result that Z qualifies as a fusion of A and B, even though it is part of both, in Goodman sense, so F3, but definitely not in the other two senses. And on the right, we have this non-extensional model. You have the Z is a fusion of the two atoms at the bottom in the Lesniewski sense and in the Goodman sense, but it isn't a fusion in the algebraic sense because it isn't the least upper bound, since Z is not included in something else that also includes, that also qualifies as including every element at the bottom. So it's a F2 fusion. So, excuse me, it's an F2 and an F3 fusion, but not an F1. So these are not equivalent. It took some time to realize that these notions have to be handled carefully. In particular, because they're not equivalent, one must be careful in axiomatizing classical mereology. Given the three ordering axioms, so P, reflexivity, transitivity, and anti-symmetry, the composition axiom schema will have the same forms in classical mereology. Namely, it will say unrestricted fusion. It will say whenever there are some phi's, there is a fusion of them. But depending on which notion of fusion you use, the decomposition axiom may vary or has to vary. In particular, the version I gave you earlier, which used algebraic fusion, had remainder as a decomposition axiom. If you use the Lesniewski notion of fusion, remainder is unnecessarily strong. So-called weak supplementation is enough. Weak supplementation says that if y is part of x, then x is another part, z, which doesn't overlap y. And if you use Goodman's notion, F3, then remainder is too strong, weak supplementation is too weak, you need strong supplementation as your decomposition principle. It's very important that one pays attention to these details. As you know, there has been some debate on this. Peter Simons, in his book, actually uses Goodman's fusions, F3, together with weak supplementation, claiming that the result is classical mereology. As a matter of fact, it is not. It's a mistake, and Roberto Casati and I inherited that mistake in our book on Parts and Places. We had to wait for Paul Hodford to actually point out that these issues are very tricky. So it's crucial that one pays attention to these aspects. Now, when properly axiomatized, the way I've just outlined, I mean, by means of these combinations of composition and decomposition axioms, of course, all differences are obliterated. That is to say, something turns out to be a fusion of one type, if and only if it is a fusion of other types. But in weaker systems, of course, that is not the case. Independently of classical mereology, therefore, an important question concerns the conditions under which a fusion of a certain type is also a fusion of another type. That question turns out to be fairly tricky. If you're interested, Aaron and I fully answered that question in our 2021 book on mereology. I'm not going to go through the details because my point here is going to be the following now. In mereotopology, in addition to these three options, there are several additional variants one may consider. For example, to begin with, instead of using parthood, or instead of treating fusion as the least upper bound with respect to parthood, one may think of fusion, or one might conceive of a notion of fusion, which is the least upper bound with respect to enclosure. Remember, enclosure is a topological notion. So X is enclosed in Z if whatever is connected to X is connected to Z. So why not consider this notion of fusion? Why not consider, similarly, a variant of Wisniewski's notion where instead of parthood you have enclosure? Or for that matter, a variant where instead of overlap in the second conjunct you have connection. Or for that matter, a variant where instead of P you have enclosure, instead of O you have connection, as in this example here. Similarly, you may consider a variant of Goodman's fusion, where instead of overlap, you have connection. And there are more, of course, because you can tinker with each individual occurrence of those relations and just change one or two of them. So the point is, there are obviously many additional variants. And here, one has good reasons to consider such variants, and we shall see one such reason momentarily in part 3 of the talk. But the question that we have, the first question is, of course, again, under what condition will these fusions coincide with their purely mereological counterparts? And secondly, under what conditions will these fusions coincide with one another? And this second question is the mereotopological analog of the question that I've just described in the previous slides with reference to mereology and the answer that I told you Aaron and I offer in our book. So these are, I think, interesting open question in mereotopology about which at the moment there is virtually nothing. You may wonder, why are these important questions? And here is the answer that I'd like to offer. They're important because it is in terms of fusion of this operator F that one defines the mereotopological analogs of the standard Boolean and topological operators. So whatever fusion you use, you may define then sums, products, differences, and complements, the mereological notions, in the usual fashion using the data description. As you see here, you may define the topological notions or operators of the interior of something X, the exterior of X, the closure of X, the boundary of X. All of this relies on some notion of fusion. So it's absolutely crucial that we get clear about that notion of fusion. It's absolutely crucial that we understand how sums defined in one sense and sums defined in a different sense relate to each other, how products relate, how differences relate, and of course, the same for any other notion. It's in terms of these operators, after all, that we can then state, for example, the usual Kuratowski axioms to the effect that something is always part of its own closure, that the closure of something is just the same as the closure of it, or that the closure of a sum is the sum of the closure. These are the Kuratowski axioms for closure. If you want your mereotopology to be as powerful as a Kuratowski topology, you better be clear about what C, lowercase c now, means. And this requires that you figure out exactly how F is supposed to work, so which notion of F you want to use. Not an easy job, but absolutely crucial. Also, it's in terms of these operators that we recover, for example, the familiar distinction between open and closed entities. X is open if it is identical to its interior. It's closed if it's identical to its own closure. Of course, similarly, if you want to have regular versus irregular, so X is regular if the closure of if it is X is closed regular if it is identical to the closure of its interior, or open regular if it is identical to the interior of its closure. All of this depends on being clear about F. And finally, it is, of course, in terms of these operators that we may fix the intended interpretation of connection. The standard notion of connection, the one that we all inherited from Bolzano and that Brentano didn't like at all, is that X is connected to Y if and only if either X overlaps the closure of Y or the closure of X overlaps Y. So typically you have external connection as a relation that holds between X and Y when one is open and the other is closed at the relevant in the relevant area. And connection is defined this way, but clearly it all depends on how F is defined. And so that's our second question to be addressed. I see that my time is unfortunately running. So under what condition can we recover the notion of a self-connected entity? So here, of course, I have in mind the big question of distinguishing between one versus two, probably the most important distinction we want to have. So one thing versus two things, or if you prefer, a thing all of a piece versus a scattered or disconnected thing. Now, the idea that you can implement in mereotopology is the following, which I find very intuitive, and most people find intuitive. An entity X is all of a piece, it's one thing, if and only if any pair of things that sum up to the whole of X are connected to each other, i.e., if and only if X is self-connected. So for example, here Y and Z add up to the whole of X and they are indeed connected. Again, X and Y and Z add up to the whole of X, they're connected. Again, they're connected. So any pair of things that sum up to the whole of X end up being connected on the left pattern, and therefore we may conclude that we're dealing with a thing all of a piece. By contrast, on the right, obviously, you can have Y and Z corresponding to the left and the right squares. They're not connected. They add up to the whole thing. So in this case, we have a scattered or a disconnected thing. That's the intuition. I think everybody would agree. It's important that this intuition can be indeed captured within mereotopology. So SC for self-connected X means that given any Y and any Z, if X is the sum of Y and Z, then they must be connected. Or if you don't have an extensional mereology and if your sums are not unique, you may just have a relational notion. Y and Z sum up to X. That's fine. Again, remember, this depends on how we define here how we define the sum operator, and here again we have the possibility of using the algebraic notion, the Lesniewski notion, the Goodman notion, and perhaps some topological variants thereof. I'll get back to that at the very end. Let me quickly point out that since connection doesn't require overlap, as we noted, i.e. things can be externally connected or just touching, this is strictly speaking a mereotopological notion. The mereological component takes care of the notion of things summing up to the whole of X. The topological component is connection. So here, there's this thought, oh, finally we have a notion of wholeness, topological wholeness, which can be added to parthood. And so mereotopology really gives us a theory of parts and wholes. If you like the topological notion of wholeness, of course, you may have a much more interesting and robust notion of an integral whole, which goes well beyond this. But if you think this is an interesting notion, I think you might say, okay, great, mereotopology is what we need. And people familiar to most of us, from Peter Simons, whom I mentioned, to Barry Smith, they all said we need topology to go beyond the limits of mereology. Unfortunately, this definition is more problematic than it might seem. In fact, it doesn't work. So I have to go quickly at this point, but there are three main worries that I want to mention. The first is that this notion of self-connectedness is well behaved only if the background mereology is fully classical. So if it's not fully classical, you don't get, for example, as a theorem, something as simple as the following. If two self-connected entities, for example, two circles or two squares, are connected, then they add up to a self-connected whole, i.e. this. It's a very intuitive principle, but there are counterexamples. For example, cases where weak supplementation fails. This is an example that Blumson and Singh, in a different paper than the one I mentioned earlier, discuss. In fact, given that I don't have much time, I'm just going to show the model. The point is, we have models where you have self-connected entities, in this case, Y and Z, whose sum is not self-connected. And the reason why here X is not self-connected is simply that X is a sum of Y and W, qualifies as a sum of Y and W in each of those three senses of sum, even though Y and W are not connected. So that's the first problem. It's not well behaved unless the background mereology is fully classical. I'm going to show you a diagram that illustrates the case. Here you may wonder, what on earth is the white portion in the middle? Well, it's not a portion. We have, in fact, a model that violates weak supplementation. So Z here only has one part, W, but it's, so to speak, bigger than W. And once you have such an entity, which of course is ruled out in classical mereology because you violate weak supplementation, you end up with a violation of the intuitive principle that I mentioned. I'm going to skip the Shiva Kleinschmidt's example of T-Rex, but if you're familiar with her 2019 paper, that would be a case in point. I'm going to skip more stuff here. Second, if the background mereology is not fully classical, then the definition may even deliver the wrong results. Not only may not deliver some desiderata, but it may even deliver wrong results. Here's an example. Suppose X is, as you see here, three circles, A1, A2, and A3, and I'm taking space here as a model of our mereotopology, of course. We want to say that X is not self-connected. After all, it consists of three disconnected circles. However, if you check the definition, it actually qualifies as self-connected because the antecedent of the conditional in the definition is vacuously satisfied. There are no two things, Y and Z, which add up to the whole of X. And so the antecedent is always false, and so the condition is always true. That's because the mereology is not classical. If it were classical, then of course we would have things such as the sum of A1 and A2, or the sum of A2 and A3, or the sum of A1 and A3. And given the existence of such sums, we would have a counterexample to the definition of self-connectedness. Because, for example, the sum of A1 and A2 is not especially connected to A3. But in the absence of those sums, which is certainly possible if you don't have unrestricted composition. Indeed, most people don't like unrestricted composition because they don't like disconnected sums, such as A1 plus A2. Well, then you're stuck with the verdict that this would qualify as a self-connected entity when in fact it isn't. And finally, this is particularly disturbing, and I'm going to conclude with this worry. The definition may deliver the wrong results even with classical mereology. That's very disappointing. And the reason is this. First of all, it may fail in contexts where the principle of monotonicity fails. A case in point would be this one. Again, it's, you might say, a fairly strange model, but it's a model of classical mereology, and it violates demonotonicity because something can be connected to X without being connected to any of X's proper parts. You might wonder, is this really a model of classical mereology? Yes, it is. It looks as though we're violating weak supplementation, but we're not, because we don't have, as in the earlier model, something that consists of only Z as a proper part. Here we have just two things, Y and Z. It just happens that X occupies a region of space, X, i.e. the sum of Y and Z, in any of the three senses, occupies a region of space that's larger. Here's a model from Gilmore and Leonard of a similar scenario. But again, given the time, I'm going to skip the details. I'm going to show you, and this is the conclusion, the really disturbing case. Some of us may be sympathetic to the notion of extended simples, so mereological atoms that are not point-like, i.e. that occupy extended regions. After all, Democritus already said that atoms comes in very forms and shapes, or shapes and sizes. So you don't have to think that atoms are always unextended. Now, you may have a mereotopology where the mereology is fully classical, and even demonotonicity and monotonicity, of course, are satisfied. So you may have, in other words, a mereotopology that is as strong as the one that I put on the table in the first part of this talk, and to the extent that it allows for extended simples, you're in trouble, because the general fact is that every atom, extended or not, is self-connected. That's immediately provable from the definition. So here's an example of an extended atom. Now, if there are extended atoms, there may be disconnected extended atoms. Why not? There are, in fact, people who claim that there are such things as the yellow disconnected extended atom that you see represented here. But if there are such things as extended disconnected atoms, then we're stuck, because this one, by the fact that I've just claimed, qualifies as self-connected. After all, the only X, Y, and Z that satisfy the antecedents are A. So the antecedent is true when Y, Z, and X all coincide with A. And of course, the consequent is also true because A is connected to itself. But the thing we have is not a self-connected whole. It's a disconnected whole. And that's really disturbing. In fact, that applies also to composite objects. Obviously, here we have an object consisting of two disconnected, extended simples, or many. And in fact, you can go on forever. You can even have gunky models which satisfy the mereotopology that we saw earlier with monotonicity and demonotonicity, Ganki models where you get the stuff that you see represented here qualifies self-connected, even though in the end it isn't. So that's really disturbing. There are many options here that one could consider. One is to redefine self-connectedness, perhaps with some help from location theory, perhaps with some help from whole theory. Location theory, because of course we're talking about extended simples. Whole theory, because you might think, for example, that the difference between the two cases can be put in terms of the complement of the relevant atom being singly or doubly perforated. This is why, again, topology might be helpful. Unfortunately, while I toyed with this idea for a while, especially because I was very happy to see the holes might be helpful here, it doesn't work because it's not that you get those descriptions that I just did in every case. So the complements might not have the features that you need to distinguish the cases, so forget about it. Besides, if our disconnected thing is the whole universe, as some Parmenidean might think, with no complement, then we're stuck anyway. Perhaps we should revisit the relevant notion of sum. Notice at the top we have S, Y, Z, X. I said there were several possibilities. But suppose you revisit the Goodman notion in terms of connection rather than overlap, for instance. Then this case will be ruled out because the circle will be connected to the whole of X without being connected to either Y or Z. So in this case, X would not qualify as a sum of Y and Z, and so the counterexample is ruled out. But unfortunately, this is not going to work for the case of the extended simple. So my suggestion, and I conclude, is to take self-connectedness or oneness or wholeness as a primitive, as with parthood. So forget about mereotopology built on P and C. Use self-connectedness as your, or actually call it wholeness as your topological notion. And so you have a theory of parts and wholes. Notice, of course, you're going to get unintended models, such as the ones that we've seen, but it is one thing to get unintended models, quite another to get counterexamples to the intended or in the or within the intended models. And I think it's much better to have unintended models than counterexamples. And this will give us mereotopology, strictly speaking, as a theory of parts, P, and wholes, self-connectedness. Thank you. I'm done with this, and I think I should stop sharing. I don't know how to do that now. Oh, I probably just go, let me see. Where is it? Yeah.